Okay, good evening, guys. We'll start the third lesson related to quantum mechanics, but I'd like to review the last one, and I want to start with the formula that was derived by Max Planck. It was E times h nu, and we said that on every metal we have small electrons that will be on the surface of the metal because they are weakly connected or tied up to the nucleus, so we will assume that there are free electrons on the surface of the metal. So if we have an incident light that's coming with the energy of h nu, so it will have some energy, and if the energy is more than the binding energy here, we call it as a work function. If the energy given is less than, in the first case, let me write that if the energy given by a photon is, less than work function, we said that the work function, by the way, is the energy that keeps these electrons on the surface of this metal. So if the energy is greater, less than work function, then no photoelectric effect will occur here. So the work function, by the way, is measured in electron volts. So every metal has got its own work function. In the second case, we talk about the cutoff frequency and cutoff wavelength. And we said that if the energy equals to the work function, we can write that h nu. So let me write here h nu minimum. So this frequency here is called as cutoff frequency. Cutoff frequency will be equal to the work function. So it's easy to find the nu minima. The smallest value of the frequency that will be needed to release the electrons from the surface of the metal. So I can write it as omega or W over h, where the h is a Planck's constant that equals 6.63 times 10 to the power of minus 34. Okay. Well, likewise, we can find also the cutoff wavelengths. We know that the energy can be rewritten as hc over lambda minimum, and that will be equal to the work function. In this case, we have two cases here. We can find the cutoff frequency. Likewise, we can find also cutoff wavelengths here. So the cutoff wavelengths here can be derived as hc over work function. So this is called as cutoff wavelengths. In the third case, of course, the energy that's carried by a photon is greater than the work function. So the electrons that are released here, in the second case, we don't have any velocity. The velocity is zero because the electrons are released, but they are not moving yet. In the third case, of course, they will gain some speed here, and of course, the mass of electron is also known. We know that the mass of electron, by the way, is 9.11 times 10 to the power of minus 31 kilograms. And of course, as great energy we have, they'll have a greater velocity here. So in the third case, I can write the conservation of energy. The energy that's given by a photon will be consumed to overcome the work function, and of course, to gain the kinetic energy of the photoelectrons. So these electrons are called as photoelectrons. Indeed, these are electrons, indeed, the real electrons, but we get used to name them as photoelectrons because they are caused by the photoelectric effect. Indeed, they are electrons, real electrons. So the kinetic energy I can write for the electron, mass of electron times speed squared that is gained over 2. And of course, I can rewrite the third expression here that is gained by that's observed from the conservation of energy in terms of lambda. I can write h nu equals h nu minimum plus mass of electron v squared over 2. And of course, I can rewrite it in terms of also lambda, hc over lambda and hc over lambda minimum plus MEV square over 2. These are all phases of this conservation of energy. One is rewritten in the in terms of frequency, and here I have rewrite it in terms of lambda. So these are all called photoelectric effects that was derived by Albert Einstein in 1905, and for that work he gets the Nobel Prize in 1905. Okay, as we go on, as you see here, first of all, we call the left side as a cathode because it's negatively charged, and of course electrons will move in the positive direction. I mean in the direction of positive place, because we have the battery that's connected on this side here. So this pole here of the tube here, of vacuum tube, of course, is positively charged, and the other side here is connected to the negative plate here of a battery, of course, negative pole of the battery. Of course, this plate is called as cathode because it's negative. Okay, that was a review for the last lesson. Now I'll come up to a new case. And suppose that now I have the electrons, okay, the energy is directed, the photons, directed, incident to the plate, to the cathode, but now the things has changed. I've changed the direction here, so that the pole here is minus here, the negative pole is connected to anode, and the positive pole is connected to this side. I know that this side will be, of course, negatively charged, and this one will be positively charged. So, of course, since the electrons are negatively charged, they will be stopped by this pole here, and the voltage here that I will use to stop it, of course, we call it as stopping potential. Stopping potential. What will be the value of this stopping potential? Of course, the stopping potential at least will be equal, is used to stop the kinetic energy of the photoelectrons. I know that the potential energy, or kinetic energy, of photoelectrons will be MEV square over 2, and my stopping potential at least should be equal to the value of kinetic energy. But I know that the potential energy, in order to get stopping potential, if I denote it by U sub S, should be multiplied by the charge, and the charge of electron, of course, because the particle that I use here in the photoelectric effect, is the electron. So if I multiply E times U sub S, at least it should be equal to the kinetic energy of the photoelectrons. It means that the E times U sub S should be equal to ME V square over 2. So my stopping potential, the value of the stopping potential is ME V square over 2 E here, whereas the M is the mass of electron. You know it already, mass of an electron, and that's the speed gained by this one, and the E is the charge of an electron. So you see here, if I have to write it in the the third case where the energy is greater than the third function, of course, in this case only I'll have the kinetic energy, so the speed will be not zero. So I can rewrite the terms of third equations that I've written before in terms of stopping potential. Okay, so I'll write here H nu equals H nu minima plus US here, or I can rewrite the same things in the terms of lambda, HT over lambda equals HT over lambda minima and plus US. So you see here, the third case here is rewritten in terms of stopping potential. Now let's come up to the example, and we'll assume that in a photoelectric circuit, the cathode inside the photocell tube is made of zinc, having a work function of 4.3 electron volts, my my work function is 4.3 electron volts. That will be more convenient if, of course, if I just convert it to the joules. I have to multiply it by 1.6 10 to the power of minus 19, so I'll get here 6.88 times 10 to the power of minus 19 joules here. So that's the stopping potential, that's the work function of a zinc plate. And the light of wavelength 2000 angstroms. I know by the way that 1 angstrom is equal to 10 to the power of minus 10 meters. So my 2000 angstroms, the wavelength, lambda here, it's not, by the way, cutoff wavelength, because I have the kinetic energy. It means that at least it should be greater, of course. The energy that's carried by the photon should be greater than the work function. So lambda here, I will write it 2000 angstroms. So it means that I'll write it as 2 times 10 to the power of minus 7 here meters. So I convert it to meters because in order to calculate it, I have to convert all the things in SI system into meters, into joules, into kilograms, blah, blah, blah. So first of all, we have to find the maximum kinetic energy in of photoelectrons in electron volts. What we have to do, first of all, I have to find the energy carried by a photon, that is hc over lambda, because I have to write the formula in terms of lambda. So that's 6.63 times 10 to the power of minus 34 multiplied by speed of light, that is 3 times 10 to the power of 8, and over the lambda, that is 2 times 10 to the power of minus 7. So, of course, needless to calculate the power, because the power is assumed to be minus 19, I'll get. So 6.63 times 3 over 2 will give me the energy of 9.95, approximately 10 to the power of minus 19 joules. So that's the energy carried by the photon. So since I have to find the kinetic energy in terms of electron volts, I have to convert the energy carried by photon to electron volts. In order to do this, I have to divide it by 1.6 10 to the power of minus 19, so that the powers will be cancelled, and I have the energy carried by a photon is appeared to be 6.21 electron volts. So if I write the equation for the conservation of energy, I know that energy carried by photon equals work function plus kinetic energy. So the kinetic energy of photoelectrons will be the difference between energy carried by photon minus the work function. So that is 6.21 minus, I have the energy, the work function, sorry, it's 4.3 here. So 6.21 minus 4.3, that will be equal to 1.91 electron volts. And that's the kinetic energy of photoelectrons in electron volts. So we solved the A part. Now if you come up to the B part, of course, I have to convert the energy carried by photoelectrons. I have to convert it to joules. In order to do this, I have to multiply it by 1.6 10 to the power of minus 19, so that I'll have the number is 3.056 times 10 to the power of minus 19 joules. And the stopping potential is not hard to calculate it, because I know that kinetic energy equals E times the charge of electron times stopping potential. So my stopping potential will be equal to kinetic energy 3.056 times 10 to the power of minus 19 divided by the charge of electron, that's 1.6 10 to the power of 19. So you see here the powers are already cancelled, so 3.056 I have to divide by 1.6 in order to get 1.91 volts here. So the stopping potential will be equal to 1.91. It means that if I have the stopping potential, suppose that then I have the circuit here, and one side is connected to the cathode, that is here, I'll have the plus side here, but my photoelectrons are released from this side here. And if I just connect it to the battery, that will be approximately 2 electron volts. or my stopping potential is 1.91. If it will be 1.91, it means that these photoelectrons will not reach the other side here, I mean this plate here, because the potential that I've gained here is 1.91, will stop them and prevent the motion of the photoelectron from the positive pole here, that is, to the negative side. Of course, it will be also boarded with a vacuum tube here, and I hope that you understand this. Now I'll try to show it to you, the total, I'll try to show the FET simulations related to the photoelectric effect here. And we'll try to use the stopping potential. It means that we'll try to change the pole of the battery so that it will be stopped. Wait a minute. Okay, the only thing that you have to keep in mind is that the energy now that's gained by photoelectrons, trying to stop it by the potential difference. Now, I will have the incident light. Of course, the intensity will be greater than 0. You see here now the photoelectrons are, in the case of 0 volts, they are reaching the other side because the current, and you see that the current is passing is 0.069 amperes here, and the incident light is 400 nanometers. Now, what if I will change, you see here, my stopping potential here is approximated 2 volts, because you see here that the photoelectrons that are released from the cathode here cannot reach the other side, because you see here I have minus 2.20 volts here that is in opposite pole, and this potential here that I show in this case is called as stopping potential, because you see here the speed of photoelectrons now slowed down and they can't reach the other side. And in the case of 0 volts, you see here, or let it be 0 volts here, I will use, and you see here in the case of 0 volts, they reach the other side without any deflection or without any difficulties, sorry, here. And if I just make it positive, you see here they will reach the other side with a higher speed, because now the side here that is on the other side of the tube here, I have the positively charged plate, and it's, of course, it's increasing its speed on the other side. I hope that you understand this. Thanks for attention. Let's go today.